Chapter 7, Molecular Geometry, Intermolecular Forces, and Bonding Theories. This chapter will be divided into three sections. The first will cover molecular geometry from the valence shell electron pair repulsion model, and also look at molecular polarity. The second section, intermolecular forces, will be a short section, and then finally we will look at valence bonding theory, and we will ignore molecular bonding theories or molecular orbital theories, which is at the end of the chapter. The valence shell electron pair repulsion model is a way of predicting molecular geometry from the electrostatic repulsions between electron pairs, both bonding pairs, which we will call bonding domains, and non-bonding pairs, which we will call either electron pair domains or lone pair domains. It is essential to know the Lewis structure when looking at the valence shell model, because a correct Lewis structure allows you to know the number of electron pairs around the central atom, or electron domains, whether bonding or non-bonding. The valence shell model is broken down into classes. Each class is designated A, B, E, with the A being the central atom, B being the number of bonded atoms, no matter what the number of bonds, whether it be a single bond, double bond, or triple bond. And then finally, E is a designation for lone electrons or lone pairs of electrons that occupy an electron domain. Our first class is the AB2 class. The AB2 class has a central atom and has bonded to it two atoms. Those two atoms are not accompanied by any lone pairs. Therefore, the arrangement of the electron domains is linear, and the bond angle is 180 degrees. The molecular geometry in any class that does not have lone pairs is the same as the arrangement of the electron domains, or the electron domain geometry. So the molecular geometry here is also linear. Our model compound is beryllium chloride, and again, just to note here, the 180 degree bond angle. In the AB3 class, we have three bonding domains and 0 lone pairs on the central atom. The arrangement of the electron domains is called trigonal planar. The bond angle is 120 degrees. This molecule, or molecules in this class, are flat, and all the atoms sit in the same plane. The molecular geometry, because this has no lone pairs, is the same. It is trigonal planar. Our representative molecule here is boron trifluoride. Angles are 120 degrees. In the AB4 class, we have 4 atoms bonded to the central atom and no lone pairs. As a result, we end up with a tetrahedral arrangement of the electron domains. The bond angle in the tetrahedral system is 109.5, and because there are no lone pairs, the molecular geometry is also tetrahedral. Our example molecule is methane, which is a carbon with 4 hydrogens. Note here the bond angle is 109.5. The next class is the AB5 class. We have 5 bonded atoms to the central atom. The arrangement of the electron domains is trigonal bipyramidal. The bond angles from the what are called the axial sides to the equatorial positions is 90 degrees, and the bond angle between the equatorial positions is 120 degrees. Again, the molecular geometry is the same as the electron domain geometry, trigonal bipyramidal. Our example here is phosphorus pentachloride. Note here the 90 degree and 120 degree bond angles. Our final major class is the AB6 class, 6 bonded atoms. The arrangement is octahedral. Sounds like a bit of a misnomer because we have 6 atoms, and octa means 8. The reason why it's called octahedral is because it has 8 faces, 4 on the top and 4 on the bottom. The molecular geometry is also octahedral, and all the bond angles are 90 degrees. Our example is sulfur hexafluoride. Here we can see the bond angles are 90 degrees. This is a summary slide of all 5 classes that we've just looked at from AB2 to AB6. Study it to put together all of the 5 classes that do not have lone pairs. In this next section, we are going to look at molecules that have lone pairs on the central atom. Lone pairs are still part of the electron domain. However, they do not show up in the molecular geometry, but they have an influence upon it. In this first one, the AB2E class, we have 2 bonded atoms and 1 lone pair of electrons for a total of 3 electron domains. If we go back to the AB3 class, it had 3 electron domains. This similarly has 3 electron domains, and the geometry is the same, trigonal planar. The molecular geometry, however, is different. When we look at it, we are only looking at the connection of the atoms and not the placement of the lone pairs, and these molecules end up bent. The bond angle typically is slightly less than 120 degrees, which we would see in the trigonal planar system. For example, the bond angle here on sulfur dioxide is 119 degrees. The AB3E class has 4 total domains, 3 bonding domains, hence the B3, a lone pair domain, hence the E, a total of 4 electron domains, so we have a tetrahedral geometry for those electron domains. However, the molecular geometry is different. Molecular geometry is called trigonal pyramidal because the base is like a triangle with the top molecule slightly sticking up to make it look slightly pyramidal, kind of a squished pyramid, however. The bond angles in these molecules are less than 109.5. For example, here in ammonia, the bond angle is 107.3 degrees. Our next class is the AB2E2 class. We have 2 bonding domains, 2 lone pair domains, for a total of 4 domains. Hence, the electron domain geometry is tetrahedral. However, the molecular geometry is not the same. These molecules are bent. Those 2 sets of lone pairs push the other two closer together. And the bond angle that we would expect to see here, though not 109.5, is much less than 109.5. In water, the bond angle is close to 104.5 degrees. Continuing on, we're now moved to 5 total electron domains. The first one is the AB4E class. Just to remind you, with 5 domains, we're going to be trigonal bipyramidal in the electron domains. However, we have one lone pair. As a result, we end up with what's called a distorted tetrahedron. The lone pair goes onto one of the equatorial positions. As a result, this bond angle here that we originally expected to be 90 is usually less than 90. And the bond angle here along the equatorial positions, which we expected to be 120, is usually less than 120. Continuing on with 5 domains, we're going to have the AB3E2 class, 3 bonding domains, 2 lone pair domains. The electron domain is trigonal bipyramidal. It has not changed. When we have 5 total domains, the electronic geometry is trigonal bipyramidal. The 2 lone pairs are put in the equatorial positions. As a result, we end up with something that is T-shaped. However, these bond angles are going to be less than 90 degrees. The steric hindrance caused by the lone pairs pushes the fluorines closer together in chlorine trifluoride. The last of the 5 domain systems is the AB2E3 class. Has 2 bonded pairs and 3 lone pairs. All 3 lone pairs go in equatorial positions. As a result, it leaves the 2 bonded pairs opposite each other, and we end up with a molecular geometry that is linear. Again, stress that the electronic geometry, that is the geometry of the electron domains, is trigonal bipyramidal. So these molecules are linear. From electron domains that are octahedral, where we have 6 total domains, we're going to put in 1 lone pair, and we got the AB5E system. Just for convenience sake, we're going to put the lone pair on the bottom. As a result, we end up with a molecular geometry that we call square pyramidal. It's kind of hard to see in bromine pentafluoride as we've drawn it, but if you look at the models below, the 4 fluorines here make a square, and then the rest of it finish out the pyramid to the other fluorine that sticks up. The bond angles here are all slightly less than 90 degrees. Our final 6 domain system is the AB4E2 class. It has 4 bonded atoms and 2 lone pairs with 6 total domains. This one is octahedral. The lone pairs are placed opposite each other. Here we're placing them on the top and the bottom. The result is a square planar system. Here xenon tetrafluoride is square planar. The bond angles are still all 90 degrees. There's no change on these. And this ends our classification for the valence shell model. As has been mentioned earlier, the lone pairs cause a steric hindrance that changes bond angles from what we would expect. Here we're showing 3 molecules that are all tetrahedral in their electronic geometry: methane, ammonia, and water. However, if we look down at the bottom, the lone pairs do have an influence on the bond angles. With no lone pairs, we're at 109.5 degrees. With one lone pair, the bond angle is reduced. In the case of ammonia, it is 107.3 degrees. And the steric hindrance increases even more with 2 lone pairs, decreasing the bond angle in water to 104.5. So, how do we predict molecular geometry? Step 1 is to draw a Lewis structure. Step 2 is to count the number of lone pairs on the central atom and the number of bonded atoms on the central atom, and then use our VSEPR geometry to predict the geometry of the molecule. Let's look at sulfur dioxide. We've seen it before, and sulfur tetrafluoride. In sulfur dioxide, if we look at this, we have 2 bonded atoms. That's the 2 for the AB2. There's a lone pair. That's the E. And if we go back to looking at the geometry, it starts out as a trigonal planar geometry because there are 3 attachments. However, one of the attachments is a lone pair of electrons, and what we see is the bent shape in the molecule. With sulfur tetrafluoride, we're going to count them: 1, 2, 3, 4 bonded atoms. That's the 4 in the AB4. There's a lone pair on the sulfur. That's the E. AB4E comes in the trigonal bipyramidal class electronically. However, the lone pairs put on the equatorial position, and the result is a distorted tetrahedron. And as I told you before, the bond angles tend to decrease. Notice here the bond angle on the equatorial position should have been about 120. It's 101.5. And the total bond angle from fluorine to fluorine from the 2 ends is 173.1. We would actually expect it to be 180 degrees. Now to come back and remind you about dipole moments in polar molecules. When we looked at bonds and electronegativity in the previous chapter, we could establish the polarity of a single bond by looking at the difference in electronegativities. We could designate an electron poor region and an electron rich region in a bond. What we're going to do next is look at the influence of bond polarity on molecular polarity. Looking at dipole moments in molecules, now the first one we're going to look at is ammonia. The hydrogen has an electronegativity of 2.1, and the nitrogen has an electronegativity of 3.0, so that these bonds all have their negative end at the nitrogen, which would indicate that you're going to have a more negative end at the nitrogen. The other thing that we have is this lone pair Lone pairs also pull electron density towards them and gives us another dipole, which contributes even more to the result, which is a 1.46 dipole. Is that a big one? Yeah, that's a fairly substantial dipole. Are we going to do calculations with it? No, we're not going to do calculations with it. The way to come up with this would be to do a little bit of three-dimensional vector analysis to figure out how all these dipoles added up together. With nitrogen trifluoride, the polarity of the bonds is actually in the other direction, indicating that we're going to have a negative end toward the fluorine. The lone pair pulls electronegativity upward. The resultant is a slightly smaller dipole moment pointing toward the fluorines at 0.24 dBs. So how are we going to look at and establish dipole moments and the polarity of molecules? Well, we could use this two-dimensional approach that you see scribbled all over this slide, where what I've done basically is I've laid out the difference in electronegativities, given these vectors direction, and then decided whether or not it was going to be a polar or nonpolar molecule. Well, this system works very well for bent molecules, like these two, linear molecules, like carbon dioxide, trigonal pyramidal, trigonal planar, and tetrahedral we can make work. But once we get up to the trigonal bipyramidal and octahedral molecules, this doesn't work as well. So basically, we're going to ignore this. So the big question is, how can you determine if a molecule is polar? You can learn 3D vector analysis, but as I say down here, not on your life. Learn a simplified 2D approach. Well, we could, but that actually takes a little bit more effort. Learn a few simple rules. That is my favorite choice, and I know that in a multiple choice you got to have at least 4 answers here. Ask Mr. Burns. Well, I know that's your favorite choice. We are going to go with C. Learn a few simple rules. And basically what these rules come down to is knowing which molecules are always polar and which ones you have to look at and determine whether or not they are symmetric as far as the electronegativities go. So I'm going to point a few out here. AB2E, always. AB3E, always. AB4E, always. AB5E, always. So that basically establishes a rule. If we have one E, it's an always. Then there are 2 others, the AB2E2 and the AB3E2. Both of those are always. So basically, if you can break it down into those sets, one lone pair will always be polar. AB2E2, the bent molecule, there will always be polar. And finally, the AB3E2, the T-shaped, will always be polar. The others, as you can see here is looking at, do we have different electronegativities around the central atom? Can we find some way of making it symmetric or not? Well, let's look at it a little bit. This is dichloromethane, CH4Cl2. Does it have a dipole moment? Is it a polar molecule? Initially, you might think that the polarity of the bonds would balance each other out, but you have to remember this is a three-dimensional molecule, and if I have different electronegativities on the bonded atoms, then I will have some measure of polarity. The chlorines are 3.0 for their electronegativities. The hydrogens are 2.1. The result is we have a more negative end on this side of the molecule, a more positive end on the hydrogen side of the molecule, and it actually has a dipole moment. And this is a polar molecule.